I'm going to be discussing some recent work we've been doing on inference of a particular type of unmodeled source, which are core collapse supernova waveforms. And yeah, so this is the outline of the talk. So I'll be talking about two different kind of signals, those corresponding to neutrino-driven waveforms, which are generic core collapse supernova mechanism for explosions of massive stars. And then our method there is based on some quasi-universal relations we have found relating the frequency with physical properties of the proto-neutron star. And that allows for asteroseismology of proto-neutron stars for the first time. And then if time permits, at the end, I will talk about rapidly rotating core collapse supernova as well, with a different type of technique that we use for this very, very specific case of core collapse supernova. These are very rare events, highly rotating supernovae. The talk is based in these papers, which are already published, if you're interested in more details, and in these two papers, which are currently in preparation. And this is a talk that can be regarded as a continuation of a previous talk in this long program, in the workshop 1 on numerical relativity. My colleague, Pablo Cerda-Duran, gave a talk on the actual asteroseismology issues. I mean, how to identify modes of oscillations of the proto-neutron star and compare with actual as an eigenvalue problem, solving it as an eigenvalue problem and compute the actual modes of oscillations of those stars. All right. So core collapse supernova, as you all know, they are prime sources of gravitational waves, because in addition, the typical frequencies are in the sweet spot of the current second generation detectors. They are perfect targets for ground-based detectors. The problem is that the amplitude is much smaller, significantly smaller than the amplitude of CBC sources. So they have to be very close by in order to be detected. But if detected, we could get a lot of information from stars. They can reveal the underlying, from the waveforms, we can obtain information about the explosion mechanism of massive stars. And we can also get information about not only the progenitor star, but also about the proto-neutron star that is produced in this kind of explosions. So the progenitors are massive stars in this range, typically from 8 to 120 maybe solar masses, something like that. Most progenitors are non-rotating. The 99% of progenitors are non-rotating stars. In gravitational waves, they are observable within about 10 kiloparsecs or so. So these would be galactic sources. And they are rare events. So typically, the typical rates of core collapse supernova explosions are one event every 30 years in our galaxy. So during the collapse leads to a proto-neutron star. The collapse of the iron core at the center of the star leads to a proto-neutron star that is unstable to different physical mechanisms, typically convection, and the so-called standing accretion shock instability, because the shock that forms is stalled and then it suffers some kind of non-spherical perturbations and is going to oscillate. And this produces, these two mechanisms produce a lot of gravitational waves. So eventually neutrinos deposit sufficient energy behind the shock and the star explodes. So I'm going to be talking about the gravitational waves that are produced in this phase due to the convection and the standing accretion shock instability in the proto-neutron star. So all the information we have about these systems are through numerical simulations, numerical relativity simulations of core collapse supernovae. So these are the results of one typical 2D simulation. And from this simulation, one can extract the time series, the waveform, the strain, and this is plotted here. So this is the strain as a function of time for 1 second of the evolution of this particular model. So as you can see, the typical waveform is highly stochastic. It almost resembles noise, right? So it's highly stochastic. Now, if one computes the Fourier transform of this signal and computes the spectrogram, the time frequency plots, we can see that for all simulations, for all core collapse simulations by different groups and with different physics, different initial data, different equations of state, so all the spectrograms all show these characteristic arc-shaped features in the spectrogram. So this is something general for all core collapse supernova explosions. So the frequency increases with time in this particular form, And these frequencies are actually associated with particular oscillation modes of the proto-neutron star, as I will discuss in a minute. So here I'm showing here on the left the gravitational wave spectrogram from a 20 solar mass progenitor that we computed in our group, and here on the right, so you can see some specific regions in the spectrogram where the power is larger, and then you can try to track these particular tracks, right? With I mean, what is the physics behind these particular features in the spectrogram? And they actually can be matched to specific proto-neutron star eigenmodes. And this is actually what Pablo talked about in his talk in the first workshop in this program. And in particular, we can identify typically in these spectrograms two kinds of modes: P modes, which are the restoring force for P modes is the pressure, the gradient of the pressure. So the frequency is related to the so-called lamp frequency, and the mode frequency is related to the sound speed, which in turn is related to the square root of the average average density in the star. So square root of the mass of the star divided by the radius of the star to the power of 3. And then other types of modes are the so-called G modes or gravity modes. For gravity modes, the restoring force is buoyancy. Okay, so modes can be stable or unstable depending on the sign of the so-called Brun-Weissala frequency. If it's positive, they are stable. If it's negative, the modes are unstable. So this is the definition of the Brun-Weissala frequency here. And the mode frequency is related to the surface gravity of the star. So the mass of the star divided by the radius of the star squared, times some constant here, which is related to the properties of the matter of the star. So here, in particular, for this particular model, I'm showing three modes, right? The 2G2 mode, so the first two, the superscript, is the L equals 2, the quadrupolar L of the spherical harmonic decomposition, the L equals 2 value. And the subindex 2 denotes the number of radial nodes across the star, right? So in this case, there would be 2 radial nodes across the star. So this is the 2G2, this is particular gravity mode. This is the 2G3, this has 3 radial nodes across the star. And this 2F, this is the fundamental mode, the quadrupolar fundamental mode, which is the lowest order pressure mode as well. Okay? So these features are visible in all simulations of core collapse supernova. So from this information, we can try to extract some of the parameters of the star, if this can be related somehow to the gravitational wave information. So these are the questions that one has to answer, which is the dominant mode in these particular simulations, and how does these modes, or the dominant mode, depends on the proto-neutron star properties. And then one can try to do PNS astroseismology, as the same way as people do it in the sun. To study the interior of the sun, people do helioseismology. We can do the same to study the interior of PNS. So what we found recently is that through numerical simulations, we could show that the characteristic frequency for the different modes does not actually depend on the specific structure of the star, the exact structure of the neutron star, but it can be estimated from general properties of the remnant. And we were able to provide fits to these mode evolutions. So these time frequency relations, or the fits that we obtain, are actually quasi-universal, because meaning by that they do not depend on the equation of state, on the progenitor star, or in the treatment of neutrinos. So the neutrino treatment is very important for this particular modeling of these stars. Now, those relations provide the potential to be used for parameter inference once an actual gravitational wave observation becomes available. So these universal relations were obtained using 25 one-dimensional simulations using 2 different codes with different treatments for gravity, for neutrinos, and so on. 6 different equations of state here, and 8 initial progenitors with masses from, 0H main sequence masses from 11 solar masses to 75 solar masses. So we track the evolution of these modes, and we try to relate the frequency of the modes to different properties of the star in this kind of polynomial fits here, where x, the independent variable, we found that for the pressure modes, for the F mode and for the P modes, the independent variable that best fits the modes is particularly this quantity here, the square root of the mass of the shock enclosed by the shock divided by the radius of the shock to the power of 3. So this is the average density enclosed by the square root of the average density enclosed by the shock. And then for the G modes, the independent variable that best fits the frequencies is the surface gravity of the proto-neutron star. Okay. So this is an example for the 25 simulations for the P modes and for the fundamental mode. So the symbols here indicate the specific values of the simulations, and the solid lines are the fits. Okay, and with some error here, 1 sigma error here. And you can see that there is some dispersion, but well, the fits actually follow quite well the behavior, right, of the frequency. This is for the P modes, and this is for the G modes, the 2G1 and the 2G2 modes. Okay, the feature that is more visible in the numerical simulations for all groups and for all progenitors is actually this one here, the 2G2 mode. This is the mode that for some reason has more power in the numerical simulations. So are these relations really universal? So we obtain these relations for our sets of simulations. And the good thing is that other people or other groups have tried to actually use our fits, our universal relations, to see for their own simulations and see if they actually work as well. And it's quite reassuring to see that indeed they work also for other groups. These are the results from simulations with this code, 3D-NS-NE code by the Fukuoka group. It's a 2D radiation hydro code using a 20 solar mass progenitor of Huxley and Heger, different equations of state, and so on. And here, Hajime Sotani is plotting the evolution of the frequency, so the dependence of the frequency with the surface gravity for 2 different modes. This is the 2G2 mode, actually. These are the results of his simulations, and this dashed line here are the results of our fits, and they are, well, within a given accuracy, but they more or less agree quite well. And if this was a 2D simulation, and even for 3D simulations, very recent results by Jade Powell, which are not yet published. She just sent these results to me last week just to see that the quasi-universal relations actually work quite well. These are 3 different models, 3D models. Again, is the 2G2 mode evolution, and you can see that the results, well, the spectrogram of the Fourier transform of the time series is given by the colors here, the yellow colors, and the blue lines here, the white lines here are the fits from our universal relations, and you can see that within the accuracy of our fits, the modes also follow quite well the expected results. So this is actually quite interesting and quite reassuring. So how can we use this information in order to be able to infer properties from an event, from a gravitational wave detection of a core collapse supernova in the future? So let me tell you what is our proposal. So in our study, we're only going to focus on the 2G2 mode, which is the main feature in the spectrograms, and our goal is to measure the time evolution of the surface gravity, this ratio, the ratio of the mass of the proto-neutron star to the square of the radius of the proto-neutron star in gravitational wave data. Our method is divided in 2 steps. In the first step, we build a model that relates this ratio here to the frequency evolution of the signal. We want to obtain this function, R of F, okay, the dependence of the ratio with the frequency. And for that, we are going to use 1D simulations that we call the model set. For this model set, we have 18 simulations. And in addition to the simulations, we will use the quasi-universal relations, okay? So this is the kind of way, this is the way that we parameterize the discretized ratio with this cubic polynomial regression with these heteroscedastic errors here. And this is the result. So in the symbols again indicate the results of the simulations, and the fit This fit here with a given error is just given by the solid line. This is the 95% credible region here. Okay, so you can see that the dispersion in the data increases for higher frequencies, but for smaller frequencies it works fairly well. So then we have R of F, and then we also need R of T, and R of T is computed from 2D simulations. So we have a test set of 2D simulations for which R of T can be known from the spectrogram, okay? And this is interesting because it allows us to validate the model and to provide the detectability estimates. Okay, these are the 8 2D simulations that we do. 6 of them do not explode, only 2 of them explode. Here, this is the location of the radius of the shock as a function of time, and 2 of them explode, and 6 of them do not explode. Okay, so we can again compute the strain for the simulations and and compute the spectrogram. And this is for one particular case for this particular signal or model. This is the spectrogram, and then we can follow the reach of the spectrum and the maximum of the frequency in the spectrogram and obtain this time evolution here. Okay, of the frequency. So that would be our exact frequency. And then from R of F, we can compute an R of T, which is an estimate using the feed that I was showing in the slide before, in the previous slide. So our estimate is given, so here I'm showing the evolution in time of this ratio. And in red, I'm showing the estimates from our feeds using the model set, okay? And in black, I'm showing the exact results from the spectrogram of the test set, okay? So you can see again that there is the agreement is not perfect, of course, but within the 95% credible interval, the agreement is fairly good. And in noise-free conditions, as this one, we are able to recover all of the cases. This is just an illustration for one particular case, but we are able to recover all of the cases within the 95% credible interval. So in order to see if this can be used for detectability, we have to do injections in noise, okay, and see if we can do the same in using noise conditions, okay. So this is what I'm going to show you next, with the same waveform for the same model, but the results are the same for all 8 models. So we inject this particular signal into 100 Gaussian noise realizations using the PSD of the advanced LIGO at design sensitivity. We assume on the one hand that the source is optimally oriented with respect to the detector. F plus is equals to 1, F cross is equal to 0, the antenna patterns of the signal, of the strain. And we also assume that the gravitational wave signal has been already identified in the data by some other means. So what I'm plotting here is the so-called coverage and the error of our results as a function of the distance. By coverage, what I mean by coverage is the fraction of values which fall within the 95% credible intervals. Values, what I mean by values is we compare the reconstructed ratio, the estimated values, with the true values, which are given by the actual numerical simulation, by the spectrogram of the numerical simulation. So this is a little bit difficult to understand this plot here. This is the coverage as a function of distance. So we have in red, if you see here in red, these red dashes here indicate the average of the coverage, okay, as the distance increases. Then we have here, this is a box plot, no? These empty rectangles indicate the first and the third quartile in the error, okay, of the estimation. And then the plus signs here are outliers. So these are of these 100 noise realizations, these are some cases which are beyond the third quartile. Okay? And this is the same plot, but for the error, and the error is defined here. Essentially, this is the relative error where the Ri naught is the discretized value of the ratio obtained from the numerical simulation. So this is the exact value. Okay? So for a source at 9 kiloparsecs, more or less at 9 kiloparsecs up to here, we have a coverage larger than 80%, more or less. okay, with an error less than 20%. Okay, so this is more or less what we could expect. We could expect to detect using these quasi-universal relations that I'm telling you about. We could detect a core collapse supernova event and infer some properties, in particular the surface gravity, for a source at 9 kiloparsecs with an error of about 20%. Okay, these are this is the takeaway message, more or less. Yeah, yeah. Let me go on and maybe you see. Yeah. So that was for one particular waveform, but the method does not depend on the waveform. This is for all waveforms. Some of them are better covered, some of them are not so well covered. But in general, except for these two particular models that for some reason do not work very well, up to 15 kiloparsecs more or less, we get these values for the coverage and the errors. This is for one single detector. Okay. Now, how would this work if we had more than one detector? We had a coherent network of detectors and we do the same approach. Well, actually, before going to a coherent network of detectors, let me show you the results for 3G detectors as well. So for 2G detectors, the coverage is good. It's about over 80% for sources up to 10 kiloparsecs, more or less. But for 3G detectors, like Cosmic Explorer and InSync Telescope, in different configurations here that we took from these papers, we see that the ratio is well reconstructed up to fairly interesting distances, up to 100 or even 700 kiloparsecs. So the number of galaxies that we have up to those distances is much larger. So the number of events, hopefully, is much larger as well. So this is an interesting science case for 3G detectors regarding core collapse supernova events. And now, as I was saying before, we can also do the same exercise using a coherent network of detectors. And we use the 5-detector network that we will have working in the near future, hopefully. So the two LIGO detectors, the Virgo detectors, the LIGO India detector, and the Kagra detector. Okay. Actually, this study has been done by a master student last year, master student in the Artemis group in Nice. Okay, so we use, in order to do this coherent analysis, we use the same method that people employ for GRBs, using the X pipeline in order to build the spectrograms as a stitching different windows of the spectrogram together. So this is for a given source at a distance of 5 kiloparsecs using, in this case, 4 detectors. This is the spectrum, the coherent spectrogram that we built. And this is how we can follow the signal track on the spectrogram, in this case using a polynomial regression, using a lasso fit on the maxima of the frequency. Okay? Again, we have here, this would be the estimated values, the exact values actually, and we can do the same exercise. We fix the source location and we vary the distance. For this particular case, we use these values for the arguments of the antenna patterns. So a right ascension of 8 hours, a declination of 60 degrees, and a polarization angle of 0 degrees. This was just chosen in order to have strong antenna patterns F plus for the LIGO detectors. So the F plus in this case is 0.89, 0.81 for the two LIGO detectors. For Virgo, it's much smaller. Okay, so this is for the single detector method that I was telling you before, and this is for the multi-detector method. So you can see that there is some gain. The gain is not really huge, but there is some gain in the results. Okay, so actually, if I show you the comparison between the two LIGO detectors and all 5 detectors for all waveforms that we have, the dashed lines corresponds to the coverage as a function of the distance for only the two LIGO detectors, and the solid lines corresponds to all 5 detectors. And you can see that regardless of the waveform, you get some gain in the coverage, in the distance that you can cover to a given precision, if you take into account a coherent network of detectors. It's not dramatic, but at least there's some gain. Okay. So in this case, I mean, this source is located in such a way that the 3 Virgo, Kagra, and LIGO India are not optimally aligned with the source. So this was a source that was already best aligned with the LIGO detector. So that's some of the situations it could be perhaps better. Now this is a core collapse supernova, the galactic center. We vary the time of arrival. So we integrate the coverage over 2 days, over 48 hours. So with 1 day would be enough, of course, but we did it over 2 days in order to see that the coverage becomes periodic after 1 day, and we get consistent results. So this is for 3 different networks of detector: Hanford-Livingston, Hanford-Livingston-Virgo, Hanford-Livingston-Virgo, and India. And you can see that the mean coverage increases as additional detectors are incorporated into the network. Okay? So the more detectors in the network, the higher the coverage, and thus the chances of reconstructing the gravitational wave signal. And this is for 3G detectors using a 2D waveform. We assume a core collapse supernova event takes place in one nearby galaxy. We have considered these 5 galaxies, which are at a distance from us, from the Milky Way, which is less, in all cases, is less than 100 kiloparsecs. So, and you can see different combinations of the detectors. So, like Cosmic Explorer 1, Cosmic Explorer 1 plus 2, ET. I remind you that ET is not just one single detector; it's 3 detectors. Or CE1, CE2 plus ET. Okay. So, and you can see that the more detectors we have in the network, the better is the result. So, if we had a supernova explosion in all of these, in any of these galaxies nearby, we have a coverage in this particular final configuration. We have a coverage which is essentially 1, so almost a total coverage. So that would be our nominal coverage in the question that was raised before. So we want to get as close as possible to 1, of course. So yeah, this is just an example for one waveform, and we are currently doing the same study for all waveforms of our sample. All right, so I still have 15 minutes to go, right? So that's great. So I have sufficient time, I believe, to discuss this other particular case. Let me change gears and discuss the specific case of rapidly rotating core collapse supernova. So I was telling you before at the beginning, this is a very specific case. Only 1% of core collapse supernova events are have rapidly rotating progenitors. So this is really, the rates for these events in our galaxy are really very, very low. So it's the order of about 10 to the minus 4 per year, events per year. So it's really something that is going to be very, very rare if we ever detect one of those. But anyway, they are much more luminous than gravitational waves than non-rotating supernova, of course. Now, in this case, the peak gravitational wave emission is produced at bounce due to rotation, because this is related to the degree of oblateness of the core, which is in turn related to the rotation rate. So this is the waveform, the full waveform of 1.6 seconds that done by Pablo that I was discussing before when I showed you the spectrogram. But the rapidly rotating core collapse supernova, most of the studies only focus on this early bounce phase, so about only 10 milliseconds after core bounce. Okay, so this is the kind of signal, early bounce phase signal that people have mainly studied. And the most comprehensive study of this bounce signal has been done by Sherwood, Richards, and collaborators a few years ago. They studied over 1,800 2D core collapse supernova models up to 10 milliseconds post-bounce. So now, if you take into account, if you consider only this part of the signal, this is an example of how the strain looks like for these particular models, for different waveforms of their sample. There are 1,800,000 waveforms. So these are different equations of state again, and there are 2 main features visible in these simulations, and these are two very important features because it's what is going to allow us to do inference. The first one is that if you look at this post-bounce oscillations, the proto-neutron star post-bounce signal, part of the signal, this is once the neutron star forms, it oscillates wildly. It rings, right? So this ring down, this early part of the signal, most of the waveforms overlap. Okay, that means that if you do a Fourier transform of the signal, you're going to have a peak frequency which is going to go down exponentially with time, similar to what happens to the case of the black hole quasi-normal modes, right? So there is a peak amplitude, so there are several oscillations with a peak frequency, f peak, And in addition to that, here by plotting all of these waveforms together, you can see that the distance from the maximum negative peak of the strain to the maximum positive peak of the strain is more or less constant. Okay? The time of bounce coincides with the maximum negative peak. So this delta H is also more or less constant. So this is a peak with amplitude delta H. So these are the two parameters that we are going to use in order to do inference of core collapse of rapidly rotating progenitors. Okay? So what can we do? What can we learn from performing parameter estimation on these two parameters, delta H plus and F peak? The answer, this is a spoiler, the answer is that we can estimate the source parameters, the central density, and this parameter beta, which is the ratio between the rotational kinetic energy and the gravitational potential energy. Okay? Which is actually quite interesting to be able to do this kind of inference. So the reason why this is possible is the following, is illustrated here. Now, if you plot some of the waveforms of this parameter delta H plus that I was discussing before, this amplitude, as a function of T over double as a function of this beta parameter, the ratio between the kinetic rotational energy and the gravitational potential energy, you can see that up to a given rotation, these are all fastly rotating progenitors, but they are not extreme. Well, there are some models that are also extreme, but up to a given rotation rate, angular velocity, you can see that this parameter scales linearly. I mean, the amplitude, the peak amplitude scales linearly with the beta parameter. And then up to that same, and if you plot the peak frequency with respect to the maximum of the angular velocity normalized by the square root of the central density of the star, you can also see that up to this value, there is a constant value of this peak frequency. Okay? So therefore, the peak frequency is proportional to 1 over the square root of the average value of the central density. So that's why if we can do inference on this delta H plus and in F peak, we can get information on the rotational properties of the star and also on the matter properties of the star. Okay? All right, so these are the two parameters that we will use to do inference, and there's one additional bit of information which is very important. So one thing we realized in our study is that it is possible to describe a large fraction of the waveform, of these 1800 waveforms, in the early post-bounce phase in a very simple form, which is a master waveform template, which depends only on these two parameters, delta H plus and F peak. So in order to do so, we have to include models. We cannot include all the models. We can only include models up to a given rotation rate, and those models are going to collapse because if the rotation rate is very large, they have too much centrifugal support that they will not collapse. Okay? And in addition, we have to align all the waveforms at the time of bounce. We have to renormalize the strain and the time axis, and we have overlapped the late sinusoidal wave part of the waveform as much as possible in order to dig out this master template. And then, indeed, it turns out that we can average 420 waveforms out of all the 1800 waveforms in the sample in order to build a master waveform. So here I'm plotting all the 420 waveforms that follow these trends. And here on the right, I'm plotting the average of all of these 420 waveforms, which is this solid line here, together with the 95% confidence level at which we can reconstruct this master waveform template. Okay? So this signal encodes the information from 420 waveforms with different equations of state, with different progenitors, and so on and so forth. By the way, this was all done, was led by an undergraduate student in Valencia last year, Carlos Pastor Marcos. All right, so we have that the waveforms the waveform model depends on three parameters, mainly on these two parameters, delta H plus and the F peak, and also in the inclination angle of the rotation axis theta here. Okay. So we're going to perform 3 series of injections using different conditions, given random values to these parameters. We will do null injections with 0 amplitude. This would be just a reference for the noise. We also will do injections of the master waveform with the values of the parameters in these ranges, the frequency peak between 600 600 hertz and 1 kilohertz. And this particular combination, because we get together the inclination angle and the peak amplitude together in this particular form in order to actually to simplify the computation. So this particular amplitude is going to vary between 0 and 700 centimeters. And in addition to that, we also do random injections of individual waveforms. So we have a master waveform which is built out of 420 waveforms, but there is no single individual wave injections of the 420 waveforms selected to build the master template. So we do 1,000 injections on random Gaussian noise of a 3-detector HLV network at design sensitivity. So, and these injections are performed at random sky location, random luminosity distance in this range, and random inclination angle of the rotation axis. And we do inference in these two parameters, as I was telling you before, assuming that the source location, that the source distance and the time of bounds are known. And we use the Bilby code in order to do this study. Okay, let me show you the results of our inference. So I'm plotting here the base factor, the log of the base factor as a function of the distance for the three types of injections. So the injections of the master template, which are shown here in these plots with the green crosses, injections of individual signals, which are shown in the plot with these blue plus signs, and noise injections, null injections, which are shown by red dots. Okay? And if you look at the signals, the blue and the green injections, you can see that for signal injections, the maximum of the base factor, the scales, or goes like 1 over the distance squared. And that sets the upper limit for the signals with a maximum amplitude of optimal inclination and sky location. So this is this dashed line here. Okay? We don't find any influence of the peak frequency on the base factor. There is no trend, no clear trend. And for the null injections, we find a base factor, a log base factor of which is compatible with 0. Okay? So in general, signals with a log base factor above 0.5 are above the noise at a 99% credible interval. Okay, so so here I'm plotting the dependence of the base factor with the network SNR. So we find that the maximum of the base factor, of the log base factor, is proportional to the network SNR squared, which is given here by this dashed line over here. So at this point here, the base factor is 100, the log of the base factor is 100, and that corresponds to a network SNR of 20. And that's a very interesting value because this was shown using the coherent wave burst pipeline. This was shown in the PhD thesis of Marek Szczepanczyk in 2018, that over 50% of fast rotating core collapse supernova with an SNR of 20 are going to be detectable in principle in real detector noise conditions. Okay?
Sorry, is that when you say log 10 base factor is 100, are you saying the base factor is 10 to the 100?
Yeah, that's wrong. Yeah, the base factor is 100. Yeah. Yeah. Okay. There's a typo over there. Yeah. Okay, so in our sample, that corresponds to over 40% of either master waveform injections or individual waveform injections. So that provides a conservative estimate of the potential detectability of a rapidly rotating core collapse supernova based only on observed data. Okay, so it's a large number actually. It's quite interesting. And these are similar to the confusion matrices, right, of machine learning. So this would be the the median of the inferred posteriors in the two parameters, in the f peak and in the peak amplitude. The inferred posterior versus the true values of the injected waveform. So here we have the inferred values in the vertical axis, and in the horizontal axis we have the true values, the injected values. Okay, and this is for injections of the master waveform, and you can see that the agreement is quite tight. So we have in red the results with a base factor larger than 100, and in gray we have the results with a base factor less than 0.5. Okay. So in the case of of signals that can be detectable, because remember that for base factors larger than 100, the SNR is going to be larger than 20, and in principle they are going to be detectable. We have that the peak frequency can be inferred with an accuracy better than 2%, and the peak amplitude with an accuracy better than 10%. Now, if we now, instead of injecting the master waveform template, we inject an individual, randomly selected individual signal, the dispersion is a bit larger as expected, but still the results are still tight to some extent. Okay, so there's chances that they could be detected as well. Okay, so the fact that the dispersion is larger in this case is because the master waveform does not perfectly match any of the individual signals that we use in order to build the master waveform in the first place. All right, so let me then move to my conclusions. So I've been discussing how to do inference of proto-neutron star properties using gravitational waveforms from core collapse supernova, and this is something that hopefully may be possible in the near future, following a successful detection, which is something that we are all expecting for. This has been illustrated with two specific cases, a generic case for most common events that would be signals that result from a neutrino-driven explosion, and also for the fast-rotating case that would be signals that result from a so-called magnetorotational explosion, but those are rare. Now, in the first case, in the generic case, our method is based on this Asteroseismology of proto-neutron stars with the use of these quasi-universal relations that exist between the frequency of oscillation of specific modes and combination of physical parameters of the proto-neutron star, such as the mass and the radius in the combination of mass over radius squared, the surface gravity, and the location of the shock radius for the central density, for the average density of the star. And then for fast-rotating core collapse supernova, we have a completely different approach which is based on building a master waveform template out of a large number of numerical simulations. And this template can be built for the early bounce phase, and this allows to perform by using inference on the peak frequency and on the signal amplitude. Now, in the near future, what we want to do is, in particular for the generic supernova case, we only use the 2G2 mode, if you remember, but there are many modes that are visible in the spectrogram. If we are able also to provide the same kind of analysis for other modes, we could expect to perhaps being able to disentangle the mass and the radius. Instead of computing the mass and the radius in this combination of the surface gravity, maybe we can separate both things, the mass and the radius, if we use more than one mode. So this is something that we want to study in the future. We also want to improve the mode analysis framework. So this is based on a linear analysis and an eigenvalue study using angular average profiles. So this is a 1D problem, essentially, and we want to improve that, considering 3D effects and rotation. And in the case of rapidly rotating progenitors, we also want to see if other waveforms for rapidly rotating progenitors obtained with other codes also follow well these trends, and the same master waveform can be used for these other waveforms. So this is something that we plan to do also in the near future. Yes, and that's all I have. So thank you very much for your attention.